All right, hello, everyone. Our names are Daniel, Kooresh, Defne, and Yousif, and our project has to do with using machine learning to photographically classify ingredients and retrieve recipes. So just as an exercise to introduce our project, imagine if you came home after a long day and found the following ingredients in your fridge: apples, cabbage, onions, and mayonnaise. Can you think of anything you can make with these ingredients? Well, with these ingredients, you can actually make a coleslaw salad. And many people without cooking experience don't know what they can make with the ingredients they have. So our app aims to solve this problem. The user enters ingredients, and they get a list of recipes that use those ingredients in response. And there's more, because as we all know, photographic apps are very popular these days. Our project takes advantage of this. We let users take photos of the ingredients instead of typing them in, and we classify the pictures automatically before suggesting recipes. And this is the machine learning part of our project. So our app makes life easier for people who want to cook with existing ingredients. And this is especially important in the time of COVID-19, when people don't want to go outside. It also removes communication and accessibility barriers between people with different backgrounds and experiences. And now, obviously, supporting every ingredient in the world is impossible, but we still wanted this app to be useful. So striking this balance was a nuance we had to address before any work could be done. So our team dug through a lot of recipes online and identified 45 ingredients that form the basis for the vast majority of them. And this turned our project into a multi-class classification problem. And then for each ingredient, we found multiple images from online databases, Google Images, and photos taken by us or our friends. And this allowed us to easily compile hundreds of images per ingredient and expand whenever we needed to.
We had to take several steps to ensure we had enough consistent data. First, we made sure each image was under the correct standardized label and used a Python script to ensure consistent square sizes. While this may be a limitation, since not all images are square, ingredients will likely still be in frame after cropping. Then, we augmented the data by applying random transformations from the PyTorch library, such as rotation, hue, saturation, brightness, etc. This created a larger training set and also accounted for users who may take pictures from different angles and different lighting and so on. After all this, we had a dataset of about 80,000 photos. This was split into a 60-20-20 division into training, validation, and testing sets, which were bashed and fed into our model. Before creating models, we did two tests to determine a rough lower bound and upper bound that we wanted for our model. So for the lower bound, we took a CNN we built in Lab 3 and we altered it to support 45 outputs instead of 11. This was a very simple model we wanted to beat, and we were able to achieve an accuracy of about 56% after some tuning. And for the upper bound, we took 20 humans and we gave them 50 random images to identify. The average accuracy for this test was about 89.3%. This was a goal for our model. As we see, our CNN gave pretty good results. We decided to combine the advantages with AlexNet, which we thought would be good for identifying ingredient features. We went through many architectures and significant tuning. After all this, we settled on the model presented in the diagram, with AlexNet connected to a single convolutional layer and a fully connected layer, spaced apart by ReLU and TANH activation functions. The final training parameters we settled are also shown on the diagram.
So we first rented a server on GCP with an NVIDIA Tesla T4 GPU, as that made our training much faster than running it on Colab. And we also used it to run our web server on, as our team created an interactive web app with a Flask backend. So I'm going to demo our web server. So first, the user logs in, and when they log in, they can do two things. First, the user has the ability to give a list of ingredients to exclude from the recipes. This functionality is to make sure recipes respect dietary restrictions and preferences. So first, for example, I'm going to do olives and garlic, and then the user can upload photos. So here you can see a clip of me taking a picture of an egg, and I'm going to take that photo along with other photos that we've taken to give it to our model. So the user submits this, and you have to wait a couple of seconds until the model runs and gets the labels back. So now we have the labels back, and we can see some of them are right. Most of them are right in this case. Potato is right, mushroom is right, egg is right, onion, tomato, and cucumber is right. But for beef, it thought it was a sausage. So what the user can do is that they can correct this, because our app also lets the user correct any errors that our model makes. This is a solution to our model's limitation. So instead of sausage, we're going to write beef. and then we're going to send all these ingredients into our recipe API. So now we have a list of recipes that we got back. So for example, if we just take a look at the first one real quick, we see that one of the recipes is minced beef and sweet potato stew. And we can see that it got most of the ingredients that we had in here. So onions, tomato, mushrooms, sweet potato, and that's pretty much it. And the excluded ingredients aren't in this list either. And that is the fundamental functionalities of our app.
As for results, we wanted to record our performance in two different ways, an overall accuracy and an accuracy per ingredient. We modified our get accuracy function to get both values. On the slide, you can see the final values of our three accuracies, which we believe are all quite high. This slide also shows the training curves, and as you can see, we were careful to ensure we weren't overfitting the dataset while still achieving as high accuracy as we could. In terms of accuracy for individual ingredients, we range from 78% for shrimp on the left side to 98% for blueberries on the right side, with an overall average of 89 to 90%. Obviously, this graph is pretty overwhelming, so we'll summarize the results both quantitatively and qualitatively in the following slides. First, comparing it to expectations. We were very happy with these results because our average testing accuracy was comparable to the human model accuracy, and even our worst performing ingredient did better than the baseline CNN. This showed that our model was effective. There were some interesting qualitative results as well. As humans, items with similar textures and patterns can throw us off. Our model seems to do the same thing. Shrimp, steak, and ground beef are some of our worst performing ingredients, and they're all pinkish red meats packaged similarly, so it would make sense our model could be confused. On the flip side, humans and models both seem to perform well when ingredients have distinctive and unique colors and shapes. Blueberries, for instance, are unique both in their blue color and round shape. Spaghetti and asparagus are two other examples. This shows that, again, neural networks and humans behave very similarly in these classification tasks.
So a few takeaways. This project definitely ended up being much more difficult than we initially anticipated, and we can only imagine how complicated deep learning can be in the real world. We learned how neural networks have varying performance for varying tasks and how similar they are to humans. So that concludes our presentation. Thank you all very much for listening, and we would love to hear any questions you may have.